Pure, processed metals like steel are thermodynamically unstable. Because of the massive amounts of energy injected into them during the smelting and manufacturing process, these metals exist in an artificial state. They constantly seek to release that stored energy and return to their most stable, oxidized form found in nature. Compare the pristine, engineered surface of a modern steel hull to raw iron ore. The ore is the baseline. What we commonly observe as rust is an active thermodynamic imperative triggered by environmental exposure. It is the metal executing a physical drive to break down. Launching a steel ship into the ocean initiates a massive, inevitable chemical countdown. From the moment the hull touches the water, the vessel begins returning to its native ore state. Ships are among the most complex engineering structures built by humans, and they operate continuously in the Earth's most aggressive natural environment. The direct physical consequence of this thermodynamic drive is the literal dissolving of the ship. Iron atoms detach from the structure, leading to severe reductions in hull thickness and critical structural weakening. There is a secondary hydrodynamic consequence. The byproducts of this degradation create highly rough surfaces that disrupt fluid dynamics around the vessel. This surface friction directly increases hydrodynamic drag. To maintain speed, the ship requires significantly more engine power, resulting in massive increases in fuel consumption. The global shipping industry spends billions of dollars annually on dry dock repairs to replace this lost metal. For naval warships, this exact process compromises mission readiness and introduces severe safety risks. To stop this destruction, engineers must map and deconstruct the continuous electrochemical circuit driving the decay. Treating the visible surface symptoms achieves nothing. Mitigating marine damage requires analyzing the ship's hull as a functioning microscopic battery. The first essential component of the marine corrosion cell is the electrolyte. An electrolyte is a conductive medium that allows ions to move freely. Seawater is a highly conductive liquid due to its specific chemical composition. Seawater contains high concentrations of dissolved salts, specifically sodium chloride. These salts act as the primary agents that facilitate unimpeded electrical current flow through the water. The second critical ingredient suspended in seawater is a vast quantity of dissolved oxygen. Physical ocean dynamics, specifically ocean currents and constant wave motion, act as a mechanical pump. They continuously deliver fresh oxygen and salt ions directly to the metal surface. Temperature variations further dictate the speed and intensity of these reactions, with warmer waters generally accelerating the electron transfer. The ocean operates as a highly conductive, oxygen-rich chemical bath specifically optimized to accelerate electrochemical reactions. Zooming into the atomic level of the steel hull reveals the specific starting point of this degradation, the anode. The anode is the precise region on a metal surface where thermodynamic instability forces metal dissolution to occur. This schematic outlines the four mandatory elements of a natural corrosion cell: an anode, a cathode, an electrolyte, and a metallic path. At the anode, iron atoms break apart. The reaction is Fe yields an Fe2+ ion, plus 2 liberated electrons. The iron atoms dissolve into the seawater as positively charged ions. This atomic departure is the literal physical definition of hull corrosion and metal loss. Anodic dissolution is the definitive engine of structural degradation, permanently stripping mass away from the vessel. The newly liberated electrons do not enter the water. They require a new destination. The ship's steel hull itself acts as the metallic path, the required conductive conduit that allows this internal electron flow to continue. These traveling electrons move through the hull toward the third component of the cell, the cathode. The cathode is the specific location on the metal surface where reduction reactions occur. Reduction reactions are chemical processes where atoms or molecules gain electrons. When electrons reach the cathode, the reduction reaction is oxygen plus 2 water molecules plus 4 electrons yields 4 hydroxide ions. This consumes electrons and produces negatively charged hydroxide ions in the water. Critically, the cathode does not dissolve. It experiences zero metal loss. Keeping the battery running requires closing the circuit via ionic flow. The newly created positive iron ions and negative hydroxide ions migrate toward each other through the conductive seawater electrolyte. Electrons flow through the solid metal, and ions flow through the seawater. Together, they form a perfect, self-sustaining electrochemical engine. Scaling this perspective back up from a single microscopic reaction to the macroscopic structure of a naval vessel reveals the true scope of the problem. A massive steel hull in the ocean does not contain just one corrosion cell. It hosts millions of microscopic batteries operating simultaneously. Slight variations in the steel's metallurgy, localized water temperature, and oxygen exposure cause different regions of a single continuous hull plate to naturally differentiate into competing anodic and cathodic areas. This diagram illustrates the natural process of galvanic corrosion across a painted hull, mapping the theoretical current flow across the ship's underwater geometry. This active electrical field seeks out areas of exposed steel or microscopic coating defects, concentrating destructive anodic reactions in localized spots. A modern ship functions as a massive grid of microscopic batteries wired in parallel, actively dissolving the vessel's armor into the sea. A corrosion cell can only operate if all four specific elements, the anode, cathode, electrolyte, and metallic path, exist and remain connected. Panel 2 of this schematic applies the basic corrosion cell directly to a steel structure, visualizing its closed-loop circuit. To stop the battery from destroying the ship, engineers must break this circuit, but they cannot remove the ocean electrolyte, nor the steel hull. Since the physical components of the circuit cannot be removed, the electrochemical behavior of the metal itself must be artificially overridden. Survival requires pumping a controlled electrical current backward into the system, forcing the entire hull to behave exclusively as a cathode. This technique is known as impressed current cathodic protection, and it is the subject of Lecture 2.